processing, right? PDF data processing. So basically, the most important comment is actually the comment I sent to you in the email. So most of the time, you just use that comment to process data using your active material or your material of interest file and the background file, right? And then you get the PDF data. There's more to talk about, but I feel we probably can switch gear a little bit from the data processing, because I think at the list of that will make you capable of processing most of PDF data at least. So we can move forward to the PDF fitting part. The fitting part, each step, in fact, you can go to a lot of depths, a lot of details, right? But I feel that something in the future, we can get some kind of a broad view in the beginning. So we cover the 2D detector integration, right, which was done in Fit2D, and then we moved on to the PDF data processing, which was done in PDF GetX3. And now we are actually moving to a state of PDF fitting. So to fit our data and get some structural parameters so that for you to evaluate, right? So the materials we were showed today as tutorial is titanium sulfide. So if some of you, in case attend the lecture on Monday, the University of Washington lecture, which actually was given by Professor Stan Whittingham, the 2019 Nobel laureate. So he was talking a lot about titanium sulfide. A little bit background is titanium sulfide was probably the should be the first cathode to be coupled with a lithium metal, and so that's kind of the material we will show as tutorial, how to look at this structure and how to process the collected data in the PDF GUI by doing the fitting, right? The files I sent you in the email are some collected data files, and that was done years ago. I think it was 2 years ago, definitely before the pandemic. So there were some restarted their interest in this material because people try to insert more lithium, not just one lithium into this structure. If you get one lithium, you get lithium titanium sulfide, basically just the sulfide version of lithium carboxide. And people realize you actually can go further, and like 1.5 or even above. So that means you get more capacity, and to a large extent, this kind of capacity can be reversible. So that translates some more advancement in terms of their energy density. Okay, that's probably the background information. You can get some idea about this material. So it's actually a famous material. It's closely related to the lithium battery. And if you can, let me share my screen.
Actually, I have one question.
Right.
So do you think I need to turn on the captions so in the recording video people can check on the captions or live transcript, this kind of stuff?
Okay, we can try. If people find that buzzing, we can turn it off, right? We can first turn it on and see how people react.
Yeah. Okay. I'll try.
Yeah. So I'll share my screen. Can you see my VESTA screen?
Oh, yes.
Okay, that's great. So you can do the same thing, right? Following me. And we open VESTA, which is a free and a very popular software. It's used by crystallographers and theorists. So people do the calculation like to use VESTA a lot because there's a lot of good visualization stuff in the VESTA. So we can open the structure I sent to you. So I think you should have this zip file, which is a structure file for the titanium sulfide. We open it. We can take a look at this structure. So this is normally what I do. Before do the specific fitting, I would look at the model structure I want to use, right? So fitting is based on the philosophy that you already have some structure that's just very close to the exact solution. So you have close lattice parameters, you have close atomic positions. So you just want to get more exact. That's the idea behind the fitting. So that's basically approximation to get more exact. You want to have a good starting point, and you want to have idea what your starting point is, right? So what I do is I would open the structure in the VESTA and check it. So here, there's some information. We can expand it, and we can check what's really said here. Okay, so this is basically saying the information of software. And here is actually some important information about the structure. So we see this is a p-type lattice. You still remember our previous lectures, we talked about the different types of lattice, right? We can have the P, which is prismatic. We only have the points on the lattice points. And then we can also have the base center, for example, like a C. C stands for actually, there's additional 2 points actually on the base, not on the face, not on every face, but only on the base, like the bottom base and the top base. So that's why sometimes you get A, sometimes you get B, but you can also get C, right? Depending on what kind of the base face you define. And also we have the F, the face center, and we can have the B, body center. Oh no, sorry, I, which stands for the body center. So this is basically the space group information about this material. Is the P 3 bar M, I'm sorry, 3 bar M1. So if you happen to have time to look at the international crystallography table and pick up some learning materials, you probably have some idea of what these notations mean, right? So this is basically, this is a trigonal system. That's why it has the -3 symmetry, 3 bar symmetry in the first place. So if there's the 3 bar in the second place, that would be a cubic. So for example, the rock salt have the space group F, M, 3 bar M, 3 bar M, right? 3 bar is on the second place. So that's the signature of a cubic. But here it's on the first place. So this is trigonal. In fact, even just looking at the structure, you already get some idea of a symmetry. So for example, look at this titanium. You see this actually is sitting in the environment of the 3 bar symmetry. So if you still remember how the 3 bar symmetry pattern looks like, so actually there's the 3 sulfur atoms in the above, and there's a, can you guys see my arrows?
Yes, yes.
Okay, that's great. So you have this 3 sulfur atoms above, and this is 3 below. So this is actually the pattern of the 3 bar symmetry. So you can already tell something about information, right? And that's definitely agrees with the space group notation. So this is first notation is about the C-axis, which is the main axis of all the trigonal or hexagonal, also tetragonal groups, right? So it's also always the main axis is defined at the first symmetry direction. So that's why it's a 3 bar. And this M stands for the mirror. And it's describing, in fact, is actually the face diagonal direction, like 1110. So for example, it can be something like this. So you can also see this is right? So if you rotate the structure a little bit, you already see this actually a mirror plane here, right? So you see the mirror plane. So it's quite symmetric from left to right. So this is the mirror plane. And this mirror plane is in the direction of 110, is actually the face diagonal. And the third one is 1. That's basically indicating there's no really specific symmetry, just there's identity symmetry. And this is for the trigonal system is like the 210. For example, if you have something around this direction, you have symmetry, then you probably have some additional symbols over here, but there's no symmetry in those directions. So there's only 1. So that explains the notation of this space group. which is quite informative. And additionally, I would suggest you to explore software Mercury. Mercury is actually another software which was developed by the Cambridge the crystal database. And so Mercury has a very unique capability, which can show you the location of the symmetry elements. So in Mercury, actually, you can see, it will show you actually that you should have the symmetry and mirror here. In fact, you also have the mirror here, right? So actually they are related by symmetry. And we'll also show you where the three bar axis stands. This, of course, is in the main axis. All those symmetry elements will be shown in Mercury. And you can explore how those atoms, they are related by symmetry. And in fact, the connectivity of those polyhedra, as I mentioned in the previous lecture, is very important about their conductivity. And the connectivity, in fact, you can also explore how they are related by this kind of symmetry. So for example, sometimes you have glide plane, and it's very likely their different octahedra, they have some kind of interconnecting the third party octahedra. So you can see how those connectivity relates to the global symmetry the crystal have, right? So anyway, this is a very informative, and I definitely encourage you to explore more. Just do not be intimidated by the abstract symbol it has. And also it has a space group number, which is 164. So as we know, there are 230 space groups in total, and this is 164. This is very close to the lithium carboxide, the cathode material. So we know John Goodenough was known for the lithium carboxide, and Stan Whittingham was known for the titanium sulfide. And in fact, they're very close. And you can already see they are actually the two ends of the one rope, right? So the titanium sulfide with starting with the non-disated version, that's the Princeton material, and you make the battery working by inserting lithium into this. So then you get one titanium sulfide, lithium titanium sulfide. And for lithium carboxide, it's just the opposite. You start with the lithiated version, which is actually high temperature stable. It's a synthesized at high temperature, it's thermodynamically stable. And you make the battery work by extracting lithium from lithium carboxide. And so actually they work in very opposite mechanism. Another interesting thing about this is, in fact, this kind of a space group is also the space group for the fully delithiated lithium carboxide. So if you extract all the lithium from lithium carboxide, then you will reach the cobalt dioxide, CO2, right? It has the exact same space group as titanium sulfide, and same structure, the same atomic positions. That's another interesting relationship about these two materials. Okay, let's move on. Further, we can see it also shows us the lattice parameters. This is a trigonal system, so we have only two variables for the lattice, because A should equals to B. Then we have only one variable, and the second variable is the C, the length of the C-axis. And the angles are fixed. There should always be alpha beta equal to 90 degree and gamma equal to 120 degree. So that's fixed. And now we get we're entering actually the detailed structure information, right? So for the lattice dimension, we have 1, 2, we just only have two freedoms. There's only two variables to tell us or to determine the exact size of the unit cell. Then we can go further and look at the structural parameters. This is telling us the locations of the atoms. So we see we have only two kinds of sides in this structure, only side 1 and side 2. And we should keep in mind that if we have only two kinds of atoms, does not necessarily mean we will have two kinds of sides. One example is the iron oxide. So like Fe3O4 we only have the iron and oxygen, right? But in fact, iron occupy two kinds of sites. So part of the ion occupy the tetrahedral site. So it's in the spinel framework is usually the 8A Wyckoff site. And some of the ion occupy the octahedral site, which is usually 16D site. So the same atom can occupy different sites. But here we have only two kinds of atoms and also two kinds of sites. And we can look at their details. So for the sulfur, this is atomic position of it. And this is important. This is actually really the key of talking about the structure, right? Why we care about atomic positions, because that really determines how the atoms are arranged. That determines how close they are, how they're connected, whether they can be favorable for conduction or they have some other structural properties. They can closely be related to the actual chemistry. So we see X and Y, they're in fact very unique numbers. You can already tell this is just simply 1/3, right? It's rounded to the fifth decimal because of their computer software. It's just 1/3. This is 2/3. So they are very unique numbers, and they cannot be changed. Otherwise, sulfur will not be sitting in this site. It will be sitting in a different site. And a lot of consequence can happen if the position changes. But the Z position, we can see it's not a very some neat number. It's not very unique. It's not some, but we can tell this is very close to 0.25, right? So in fact, if it's exact 0.25, the symmetry of the whole system will be even higher because it's occupying a very special position. And here it's very close to 0.5, but deviates from the 0.25 special position. This is some kind of a number that can be refined to locate the exact position of sulfur. And in fact, if you look further about titanium, you'll see that titanium has all the special numbers for atomic position. They are all 0. They cannot be changed. If you change this site, and a lot other things will change consequently. So even though we have two atoms, but only one parameter is needed to know the exact structure of this whole system. In one sense, that's the beauty of crystallography, right? So we have such a large ensemble of atoms, but we can describe them with use very simple and efficient language. One thing is about space group, which tells a lot of things about the symmetry. The other thing is this kind of atomic positions. So even though we have two atoms, we just need one parameter to really get us to know what's the exact structure of this material. So that's really the beauty of the crystallography, I think. And furthermore, we see this here, this stands for the occupancy. So they are fully occupied. That's why we have 1. And this stands for the B value. The B value is something close to the concept of like a Debye-Waller factor in exact fitting. So if you happen to have done exact fitting, you are familiar with Debye-Waller factor, right? So it's kind of a approximation of thermal vibration. In crystals, in fact, the atoms, one thing, they are not just staying still all the time. They are vibrating. They're deviating from this perfect, or we can call it equilibrium position all the time. It's vibrating very fast, but it's still vibrating. And this kind of a thermal vibration causes some kind of a disorder, sometimes also referred to the thermal disorder. But there's another disorder, which is actually the static disorder, because not all the atoms, they're exact at this position. In fact, if you, let's say you count 1 billion atoms, they would form some kind of a Gaussian distribution with the peak at the exact position. But other atoms have this kind of a distribution forming a close to Gaussian distribution in terms of deviation from the perfect site. And because they are both can be approximated by Gaussian, so there's this B value can be used to describe both this kind of a thermal vibration and also the static, their disorder, which are all integrated in this B value. Right. So that's about the significance of p-value. But sometimes if you do use other software, you see the UISO, and they can be calculated through some very simple relationship. You can simply Google it and you search p-value or the UISO. You'll see the relationship before them. That's simply just a linear relationship. Okay, this site is a Wyckoff site. We probably have already covered this in the previous lectures. And this is basically telling us the multiplicity of this site. So 2 means that if we put an atom in this site, this 2D site, which have this kind of a atomic position, 1/3, 2/3, and this some number close to 0.25, then this symmetry elements, remember we have like 3-bar symmetry elements, we have the mirror symmetry elements. All the symmetry elements will act on this atom and will generate 2 atoms in one unit cell. And these 2 atoms include the original atom itself. So that's why it has 2. And D is simply some kind of a letter to differentiate from other sites that also happen to have the multiplicity of 2. For example, you can have another site which also have 2 multiplicity, but it will be denoted as, for example, 2A or 2B and 2C. So it's basically a differentiation. And also this gives the side symmetry. So if you have atoms sitting in sulfur, you have this kind of a side symmetry, meaning that the local point group is actually the 3N, right? So this, and this is 3 letters, 3 denoting the main axis, M denoting the diagonal, and the dot denotes actually this kind of a direction, which has no symmetry. That's why there's dot here. So it's always the 3 directions denoting the symmetry. This is regarding a specific point. The same thing is for titanium. You can analyze titanium in the same way, and you see Wyckoff site for titanium is 1A, meaning that if you put titanium in this position, even though the symmetry element acting on it, it will not generate additional titanium in the unit cell. There's only 1 titanium. The reason is that the 3-bar axis goes through the titanium, the mirror goes through this titanium. So whether you rotated the whole system or you actually using the mirror, it will not generate anything because this position is so special. It's lying on the intersection of all the symmetry elements. So nothing is generated after you apply all the symmetry elements. That's why the multiplicity is so low. But from here, we can already see we should have 2 sulfur atoms in the unit cell and 1 titanium atom in the unit cell. That explains the stoichiometry is exactly what we expect. Sulfur titanium should be 2 to 1. So this kind of understanding, I think something you can check, right, to make sure everything should be fine. The stoichiometry is fine. They're in their good Wyckoff site position. Okay, before we move to PDF GUI, just one last word about their the structure is actually their stacking. So let me zoom in a little bit. Okay. I'm not sure if you can tell their stacking sequence of the sulfur, but in fact, this is a HCP, the hexagonal closed packing system, because you see this is A, this is A, this is B, and then we move back to A, right? We see this pattern is the same as this pattern. This is basically the HCP packing. In HCP, it's always A, B, A, B, A, B, right? But if you look at their lithium carboxide, let's check here. So if you look at the lithium carboxide, you see it's not HCP. You see this is, let's say this is A, you have B, you do not have A here. A should be here, but it's not A here, it's actually C. So it's actually ABC, which is a CCP stacking, which means when it's lithiated, actually you will have the CCP stacking. And if it's delithiated, it will actually have HCP stacking. If you still remember our previous lecture, you remember that I mentioned HCP stacking is very rare in the listing cathode, because in HCP, you will have the phase sharing between this cation, and if you have cation in this layer, these two cation will phase sharing and a lot of repulsion. Only when you extract all the cations in this layer, you're creating their whole vacancies. Then there's absence of the repulsion. Then you can have the chances to encounter this kind of HCP stacking. So the idea is just keep in mind these things, the connectivity, the atomic position, stacking sequence, always something that you can think about when you look at the structure. The structure itself is not boring, I would say. Okay, now let's move to PDF GUI. We already checked the structure of our model material. I think I need to re-share. Let me stop share first. And share my PDF GUI. So has everybody succeeded in installing PDF GUI? Okay, I see some hands up. Okay, that's good. So I think, I assume everybody has succeeded. So likewise, as what we did in VESTA, you can open PDF GUI and we can start experience on this software. So PDF GUI is also written by the Simon Blanch's group. So you can see a lot of his names. There's definitely one of the pioneers of the PDF technique. And that group wrote this software. It's easy to use. It's based on the Python. And there are more complicated versions of it. You can check the websites for updates. So here, I think, can you see my screen? PDF GUI screen?
Yes.
Okay, good. So we can talk about the process of the data feeding. So when how about this? Let's first you right click here, you do the new fit, and so now you have you're basically starting a new project. Then you can insert the face. Say you can say titanium sulfide. Okay, it's imported, and then you integrate the data set. So this is titanium Princeton. Okay. Before we do the real fitting, we can look at what we're really doing here. So we imported our model structure, which is starting point with titanium sulfide, as we just explained. And in this structure, it has all the lattice parameters. A equals to B, and the C is the second lattice parameter, and the alpha, beta, gamma, they're correct. We'll explain this part later. And here is the structural information. So you get the sulfur and titanium. And you remember the Wyckoff side for sulfur is actually 2D, which means in one unit cell, you should be expecting 2 sulfur atoms. And that's exactly what has been done here. So this is original site. This is what you see in the VESTA software or in the SIF. And this is the additional sulfur atom that is generated by the application of the symmetry elements. So the software is actually doing all this stuff for you. Once you get to the correct symmetry, you get to the correct atomic position, it will generate all the other atoms in the unit cell. So you have 2 sulfur atoms. And this is something I mentioned before, UISO. UISO means isotropic atomic displacement parameter. So this is basically anisotropic. That's why you see this U11, U22, U33, U12, U13, U23. This is basically this is a tensor. It's not just a vector. This is basically a tensor. It's a 3x3 matrix tensor. So most of the cases when you're dealing with X-ray, you probably do not want to get too complicated and forget about all this U12, U13, and the U23. You simply focus on this 3 part, which is the isotropic displacement parameter. You can make them the same. So here they're not the same, but you can, let's say, you can change the value and make them the same, and do the same thing for other atoms. 0.05, 0.005 is a good value to start with. It's good enough. It's a very good approximation for the transition metals. For the for titanium, this value is good. For sulfur, it could be a little bit more. Let's say somewhere like 0.09 or even 0.1 could be valid. So that's about the value. So for titanium, we checked. We have only one titanium unit cell, right? It's just sitting at a very special position. So there's no additional titanium in unit cell. There's only one titanium, and the same thing. We can just get rid of them on 0. And this is OCC basically stands for the occupation. This is the site occupation of those atoms. Okay, so this is about the structural input. The PDF GUI is doing something for you, for example, generating additional atoms in the unit cell for you, and also have them prepared with all the structure information prepared here. Let's move on to this file. So this is the data file. Remember, GR is actually the RSpace PDF data. So this is data file we'll be fitting against. And when you input this data file, several things appear. We can check the tabs one by one. So is this indicating the type is X-ray? So if you happen to have collected the neutron PDF data, you can switch to neutron. And once you switch to neutron, the software will compute the pattern in a totally different way, because we know the neutron scattering and X-ray scattering, they have different numbers, not just different numbers, but different mechanism, and also the other differences. So if you switch to neutron, a lot of things will change. And data sampling is basically how the data are spaced. When you process data, your data may not be evenly spaced. So your data points may actually be more dense in one part and more scattered in other parts. So that's relates to how, when you input data, how this software will process your data a little bit, actually, by resampling the frequency of your data sampling. So this is a data range, and this is the data range of the original data, and this is a fit range, which means at what range you want to fit the data, right? So normally we can check how the data looks like. You click on this button, which is a plotting. So this is how the data looks like. So this is a typical PDF data. We see this kind of a slope, which is indicating the background for the PDF, this kind of slope. And we have this kind of oscillations, right? In fact, the oscillation, if we go further, we only stop at the 30 angstrom. If we go further, we'll see they will have the series decay in the signal. And that's something determined by the instrument. We'll discuss what instrument that means. And also relates to the structural parameter. We'll discuss them later. So this is the general trend of how the data looks for PDF data. And we see these peaks. And if we zoom in here, this is a lower region. So we see here, we have some peaks around 2.4. That's the titanium sulfide peak. So we had titanium sulfide correlation. And this is the titanium correlation, which is about the 3.4, right? So this kind of a correlation. In fact, there's some interesting facts about them. If you compute the ratio of bond lengths between these two peaks, for example, this is 3.4 and this is 2.4, you get some number. In fact, you can calculate the bond angle of that local entity. I do not want to go to details, but you think about it and you think you can figure it out. You can take my hint and go further. In fact, this kind of ratio give you a hint of the bond angle, right? If you think about the triangle, actually that's bond angle it will have. But anyway, let's get back to the data. So this is the titanium sulfide, this is titanium, and the further peaks, they typically have some kind of overlaps, but this probably corresponds to the titanium to a very further oxygen, this peak. And other peaks typically would have several overlaps, several correlations overlap together. So these two peaks normally are isolated and corresponds to single correlation. But we do observe some additional oscillations here, and these are the Fourier transform ripples. So as we discussed, ideally you should get the infinite Q range to do the Fourier transform. And that's the requirement of the Fourier transform, right? It's actually from the negative infinite to the positive infinite. But in reality, we do not have the luxury of go to infinity. So we typically want to increase the Q range as large as possible. So typically for XPD, you might get 23, which is already very good. But still, it's limited. You get this kind of Fourier transform ripples. Those ripples can be dealt with in a more in-depth data processing. If we can have arrange another lecture discussing about them in the future. But at this stage, you realize they're not part of your real data. They have nothing to do with the structural features. So you probably do not want to take them into consideration to the fitting. You can start somewhere around, let's say, 2, right? So we can change the number. Fit range, let's change to 2. Okay, and we plot again. So now you're basically asking the software to, okay, so now we do not have some Fourier transform ripples. We have all the structural oscillations. And you're asking the software to fit in this range using the model structure. Okay, that's the range. And the spacing is basically just the data points, the step size in the data. So you see already here, if you just hover your cursor around this place, it gives you some hint about what this number is about. Okay, the scaling factor is simply just a linear relationship, like how large you want to expand or shrink your data. This is just a very simple scale. And Qmax is it comes from the data itself. It's basically the Qmax you used for the Fourier transform. So as I mentioned, 23 is very good. 22 is already good. So 22, we can live with it for most of the cases. Qdam is the important parameter we'll be discussing, and also Q broad. And this temperature do not have some real relationship with the fitting. It's simply telling software, and also maybe reminding yourself what kind of temperature was this sample measured, because sometimes you want to do a sequential fitting and the data was measured at different temperatures. So you want to remind yourself and also tell the software what temperature this was collected. And also sometimes you have a different doping levels. Likewise, you do the series of fitting, you have a different doping levels. You also want to put in the number just as a reminder. It has nothing to do with the fitting results. Okay, let's talk about this Qdan and the Q broad. So as I mentioned, if we look back to this data, so this only we go to like 30.
Yuan,
yep.
Can I ask a simple question here?
Yeah.
So could you please take an example for the doping here? So what kind of case we want to use this doping, this parameter here?
Doping is just for the record of information. So for example, let's say you have lithium carboxide, right? And then you dope, let's put in some big atom like let's say lanthanide, or let's say you want to put some big atoms like let's say the potassium, right? You want to replace lithium with potassium. Then you're doping. Then you can increase the level of doping. So you have different levels of potassium. You can study how this kind of doping influences the local structure, right? You probably that will induce some local distortion around your cobalt octahedral. But those things are done during the specific fitting. So let's say you have 3 levels of doping, like 0.1, 0.2, and 0.3. You simply just make a note here. And then when you do the sequential fitting, you input other data, or you can tell yourself, oh, this is the 0.1 doping level.
Okay.
So this is just for recording the information. It's not related to really how the data is processed.
Okay.
Yeah, the same thing is for temperature. You can remind yourself, oh, this data was taken like room temperature 300K, and that was taken like 200K, that was taken 100K. Then when you input all the files, you have multiple files here, you can remind yourself, oh, this is
Okay.
yeah.
So it doesn't affect the fitting of the data, right?
No,
Okay.
it has nothing to do with the fitting. Yeah.
Okay.
But
Thank
it
you.
also has another feature, because in the future, you can plot your result as a function of the doping level. So for example, you fit the 3 doping cases, right? You want to see, okay, I want to check how my transition metal oxygen bond length varies as a function of the doping level. Then you can plot here. And the plot provides you with the capability to choose doping as the x-axis.
Okay.
So that's the meaning of these 2 parameters.
Okay. Thank you.
So yeah, we talk about these 2 parameters, which are important, and about QDAM. As I mentioned, we only have 30 Armstrong data here, but already you see the decay trend, right? So it's actually a strong scattering, strong peaks in the beginning in the low R range region, and in general, it's decaying. In fact, if you go further, like let's say 50 Armstrong or 100 Armstrong, you have a very weak peaks, weak PDF peaks. So this kind of damping is actually contributed by 2 parts. One thing is comes from the sample itself. So as we mentioned, you have so for example, the size effect. Your sample may be a very high crystalline. Let's say you only have like 10 nanometer material. So you would not expect some structural features even above 10 nanometers, right? So probably your data will decay very fast, and you have a very weak signal, even let's say above 10 Armstrong, you will not be able to see anything. So that's something coming from the structure. But another important thing coming from the instrument, because the instrument itself actually has limited the resolution. In here, the resolution we're talking about actually how well the XRD peaks are resolved. We still remember PDF comes from the XRD. That's why we do the PDF, the integration, right? We measure the diffraction data, and then we move on to the R range. And if you look at the PDF version diffraction data, you will see that those peaks, they have a huge overlap. Right? This is imaginable since you are placing your 2D detector so close to the sample. You want to get a high Q, but this is at the compromise of angle resolution. You will not be able to resolve the peaks. So if you go to the other end, for example, if you go to use a point detector and you go to APS, you use the 11 BM, you have very well resolved peaks, very well resolved, and that helps you to solve the structure. But for PDF, those peaks are not resolved, a lot of overlap. And when it's transformed to the Fourier transform and goes to the R space, the consequence you will have this kind of decay of the signal. So this kind of relationship between their peak resolution and the decay of PDF peaks is actually intrinsic. It's simply a mathematical relationship, so something you cannot avoid. But also that's also the motivation why, let's say, there are some neutron beam lines. They want to develop a high resolution, the diffraction, so they can get a very high Q, but not at the cost of losing your peak resolution. So they can collect a very high Q, let's say to 30 Q range, but still your diffraction peaks are very well resolved. And the benefit of that, you will have a very little decay over this PDF peaks in the long arc region, you will have them have strong oscillations, let's say even up to 100 angstrom. If your structure is ordered in that domain, you will have this much stronger oscillation. So anyway, the point is, it has two contributions. One is from simple, the other is from instrument. And the instrument part is something we need to deal with. And in fact, most of the times, different beamlines would have a different instrument parameters that relates to how the beamline is set up and those things. So typically you would have a different parameters. And that's just also true for this Q broad. Q broad means that actually when you the PDF peaks, they have their intrinsic width, right, which is actually closely related to how ordered your structure is. But also it has contribution. It has a broadening from the structure itself. It also has contribution from the instrument. The instrument is also contributing to the broadening of your PDF peaks. And so the instrument is playing part in these two sections. And the way to deal with them is to measure a standard. That's why I sent you the Nico standard PDF data in the email. Why we use that? That one is used to do the fitting on the Nico, so you can obtain the two instrumental parameters. They're not fully instrumental, right? But they do have the instrumental contributions, a large part, and for these two parameters. And these two parameters are very good beginning, are the very good guess numbers for you to fit your real material. So I think if you look back, you probably already get some idea that standard is important. Standard appears everywhere. It appears in our calibration of the distance in the 2D detector. Also, it actually also appears here when we do the PDF fitting. In fact, if you do the exact fitting, right, you also there are some parameters you want to fit against the model structure, which is also some kind of standard to get some of their fixed instrument parameters. So standard is important. And this is also an example of the importance of standard here. We have already measured Nico. Nico is highly scattering, is very strong scatter. Just a note of caution that you always want to turn on the filters when you measure the Nico, otherwise you will damage the detector. And also you can just measure like 10 seconds or 20 seconds of Nico and save that PDF file. Of course, you have to process it in Fit2D first and then save it as PDF file, and then use the Nico data to get this two parameters. Okay, I think we probably still have time today for doing the Nico standard fitting. So I'll close this. I don't have to save this. I'll share my screen again. And we'll move on to the Nico standard fitting. Okay, let me see. I assume you can see my screen, right? If you don't have no reactions, I assume you can see it. Okay, so we do the same thing, new fit, but this time we're fitting the Nico standard. And we insert the face. Nico. So I'm sorry, I think I forgot to send you the Nico file, but Nico file is very, very simple. So we can start from scratch since I didn't send you the file. Okay, we can start the whole scratch from Nico. You can keep in mind, Nico is based on FCC structure. It's highly symmetric FCC, and Nico is a face-centered cubic. So actually, Nico is sitting on two positions. So one is the origin, the 0, 0, 0, right? And the other is actually sitting one of their centered face, which is a 0.5, 0.50. And then you simply expand this whole structure. Okay, let's see. Just bear with me 1 minute. Okay, So new, can you guys follow me, right? You can see it, right? I assume you can see it. So lattice parameter, I just checked, lattice parameter for nickel is around 3.525. 3.525. Okay. Right. So that's the lattice parameter, and this is cubic. So everything the same. And nickel is just a yeah, I'm sorry, I just checked the structure. There was a mistake I made, and there's only one nickel site, which is actually 0, 0. We expand the nickel here, clarifies nickel, and we expand the whole structure. Space group is very highly symmetric, so it's somewhere down to the bottom. It's FM3M, right? It is. Okay. So now we have their expanded their nickel structure. So nickel is actually belonging to this FM 3M space group, and there's just only one nickel site, and there actually the symmetry will generate all the nickels in this unit cell. We can put them at their 0.003 is actually okay, and these are 0, they are good numbers, and this is 1. Okay, and then we can rename it as a nickel standard. And then now we can input the data file I sent you in the email. So, okay, we can plot it, see. So nickel is very nice. We already see the very small Fourier transform ripples. Not surprising since nickel is such a high scatter, strong scatter and nice data. But we can still actually cut off somewhere from there. We can cut off somewhere from here. The let's say 2.1 something. Okay, and we can fit to 30 degree to 30 the R space. Okay, we'll fit this number, but there's some good guesses. Typically, this is somewhere maybe 0.04, and this could be 0.02 or something. We'll fit those numbers, but they are a good starting point, and we just leave these numbers the same. And now we are trying to define. Okay, this is about how to do the technical fitting. So just keep in mind, we go to constraints. This is where we define what parameter what we want to fit, right? So it gives us the possibility of fitting scale factor, Qdam, and Qbroad. And these two are what we are interested in. And this is simply a scale, just a coefficient. What I normally do is actually I would define it at 100. Why I do this? Because we need to save some numbers for their structures, and this is a little bit trick, right? You will see that you will be defining, you'll be meeting with several numbers, and it's very easy to lose track of which one corresponds to what physical meaning. So what I do is normally I use 100, reserve this one for the scale factor, and I use single digit like 1, 2, 3 for lattice parameter. So when I look at the final fitting sheet, the list, when I look at 1, 2, 3, I know of those lattice parameters, and I reserve their double digits for their thermal parameters or for their atomic displacement parameters. So normally I would define like 11 or 22 or 33. So when I look at them, I know they are related to the atomic displacement parameters. So that's my personal way of keeping track of their getting their information organized. You can come up with your own way. You do that. And for the Qdam, normally I would use some big number, let's say 301, and this is a 302. Also, I put them as big numbers is at a hint that those parameters will be fitted at the kind of like a final stage. Yeah. And this is based on a linear fitting. It's not, it do not have the flexibility actually to go everywhere. So typically we have to use some strategy for this kind of a linear fitting based algorithm. We typically want to start with some nice behavior parameters. So who are the nice behaving parameters? Scale factor, because that's simply a coefficient number. It does not actually cause instability. And lattice parameters, and they behave pretty well. So lattice parameters typically are defined with small numbers. Also hinting that I will refine them first. And then you have some like atomic displacement or the p-value. They are not behaving so well. They can cause problems if you fit them at the very beginning. So typically I reserve them at the second or the third and during the fitting process. Okay, but about the instrument, so this is basically the three parameters we define we want to fit, and this is a scale, this is Q-dam, this is Q-broad. Okay, and then let's move to the structure. We only have one parameter for last parameter, right? We just need to know the A value. Then that's it. Then the unit cell dimension is fixed. So we just define it as 1, and same here, and same here. If we do not define anything for alpha, beta, and gamma, we're simply saying they're fixed numbers. They are not be refined. They're just always 90 degrees. And like I said, once I define this last parameter using single digit, typically I move on to actually this atomic positions or the B values in this section. So we can see there's no really atomic positions for us to refine. As I mentioned, this is a very high symmetry structure, and we have the nickel sitting at the special position. You can see the symmetry elements generate the all other 4 nickel, but they all have the very special atomic position, which is not surprising. They are all on the faces, right? So they are fixed. There's no atomic position to value. So we do not need to care anything about this atomic position parameters. And that's also that's the why we prefer to use nickel as a standard, because you have only very few parameters to care about the nickel materials itself. One parameter for lattice dimension. You have no parameter to care about atomic position. Some B value to care about, so only 1 and 2, right? You have only 2 parameters to care about the structure. And all the other informations can be used in the advantage of fitting the instrument part. That's actually the philosophy of fitting. When you want to calibrate the instrument, you always start with a simple structure. So you can use all the observations toward the advantage of the instrument rather than actually struggling with the structure materials itself. So nickel is simple and is preferred standard. Okay, so no atomic position needs to be refined. And we, as I said, we're define them as isotropic, meaning that U1, 1, 2, 2, and 3, 3, they are the same. And we use the same, just one number for them, right? So what I do is normally I just want to define, right? So 2 digits, same number is what I personally reserve for their B value. And we do not have to care about this part. They are all special positions. But we need to look at this part, which we didn't touch upon previously. And here we also have the scale factor. This is simply another coefficient. It's mostly used when you have the two-phase fitting, right? When you have two-phase, you probably want to set a scale for this one and set a different scale for another phase. But here we have only one phase, so we do not have to care about this. All the coefficient variation will be taken care of the 100 parameter that we defined at the very beginning. And this delta 1 and delta 2, so if you hover your cursor around, you'll see it says linear atomic correlation factor, right? And this is a quadratic atomic correlation factor. It's a atomic correlation factor. It contributes to the narrowing of the, to the narrowing of the first peak. Let's say, let's still look at this data. Oops, sorry. Okay, so in fact, this peak turns out to be narrower than what it's expected to be. So if you compare it with other peaks, this peak appears to a little bit narrow. It's not easy to discern by the eye, but actually through the detail of their study, it was shown that actually this peak is some kind of a uniquely narrow than other peaks. And that relates to the atomic correlation. That's why that parameter was termed as correlation. And that kind of a correlation can be dealt either using the linear way or the quadratic way. And this are defined by these two parameters. I'm sorry. They're delta 1 and delta 2. I typically would use delta 2, but you can also delta 1. It doesn't really make much difference if your fitting is robust. And typically, I would use somewhere around 2 as a starting point. And this is a good approximation in most cases. And this p diameter is basically describing the size of the particle. For example, if you're dealing with a nanoparticle, you can define the spherical shape of the particle. But here we're using a very highly crystalline nickel, so we do not have to care about this parameter. And this parameter and this parameter do not have to be used for the nickel's case. You can check the manual or just simply Google it, and you can search the detailed definition of them. They are not very frequently used, and that's the reason I do not intend to cover them in detail here. We have mostly the good initial values set, and we need to fit this number, right? So we need to define it. Delta 2. Let's say we use the, let's say it was 200. Okay, so we have defined several parameters. We can go to fit and just see if we can still remember what parameters were defined. As I said, I always reserve single digits for lattice parameter. So that's lattice parameter for the nickel unit cell, right? So that's A value or B value or C value. And I reserve the 2 digits, same number for the B value. So this is basically the B value for the nickel, and it's isotropic. So that's why there's only one number. And as I said, I always reserve 100 for the scale. So this is basically the scale factor. It's simply a coefficient to be varied. And 200 is the correlation factor, and to account for the narrowing of the first PDF peak so that's the correlation factor. And this two normally are very big numbers, and is normally what I reserve for the final stage of fitting. These are Q broad and Q dense. This is what we want to fit to get numbers that are related to the instrument. Okay, we start by having everything fixed. As I mentioned, we want to start with nice behaving parameters, which is this one and this one. I'm sorry. Should be this one and the scale. Yeah, the lattice parameter and the scale factor, they are good behaving parameters. We'll start with them. And we're back to the full range, and we can start the fitting. Okay, it can finish very quickly. So in fact, there's some information here saying that we got an RW of 0.26, which is not very bad. And this is the refined parameter, a little bit deviation. We can also see the refined parameter here, how much it deviates from our starting point, right? So the scale has to be decreased quite a bit. And we can go further, as I mentioned. And now we first copy refine to initial. We'll accept it. So they're accepted as new initial values since they are more realistic, they're more close to the real structure. And we carefully will let go of this B value. So let's click again. Okay, so you already get a very nice fitting. I don't know if you can see the plotting window, but I assume you can see on your own software, right? You already get an RW number, which is around 0.068. I don't know if you get the similar number. You should be getting a similar number if you use the same approach and do the same thing and apply them all. And now we fit this correlation. Okay, it's done. It's done very quickly. And this correlation is fixed to be around 1. Okay, let's accept more. And now this is the final stage. We want to fit the Q broad and the Q dam, right? We uncheck them together and we do the final stage fitting. Okay, it's done. So we get our probably the best fitting you will ever get in your whole PDF fitting experience. You will never have this kind of data for other samples, and you will never reach this kind of quality of fitting. So yeah, do not really buy it thinking that you will get this kind of fitting quality in your future. There's no way. This is simply we're fitting the standard. But you see, we finally get our RW value, which is around only 3%, 0.03. I don't know if you get the same number. And here we have all of them, the fitted. We have the fitted structure, which is simply A. We have the fitted B value, which is reasonable, 0.005 for nickel is quite reasonable. And the scale, and we have the correlation. So the final correlation is at 1.8. In fact, it's very close to the to the number 2 we put in the beginning, right? So that's a pretty good guess. So these two numbers are important, and we should keep in mind of this. And we can either write it down 0.035, and this is a Q broad is 0.01, and save those numbers for your future fitting when you deal with your restructure. In our case, the titanium sulfide, you put those numbers at the initial guess. That's very important. So that once you have a good initial guess, you will have a high fitting quality. So you put them as there, and also you can make a note. This is the more specific to the XPD data. And the values can change over time. So what you get this year probably was different from last year. So it doesn't hurt to actually fit from time to time on the nickel standard and get an update on this 2 parameters. And this is specific to XPD. And you measure from, let's say, 11 IDB or some other beamline, you are very likely to get the different parameters. So, okay, I think we already talked about 1 hour, more than an hour, and we only, even though only cover the nickel standard, but I think we spent quite some time exploring the structure of titanium sulfide, and particularly that's about the information to extract from VESTA software. So we might well stop here. We probably can save the fitting on the real titanium sulfide data for the next one, and we can go further from there.